Hello, everyone, and welcome to The Vertical Space, a podcast at the intersection of technology and flight. We are your hosts, Jim Barry and Luka Tomjanovic, and here we look at the most important forces shaping the market of advanced air mobility, with a particular focus on why and how they matter to those building a business in this very exciting and growing industry.
If we can pick a point in the future, let's look 5 years out, 7 years out, 10 years out and say, this is where we need to get to, NASA can take on some of the really hard challenges and work through those so that by the time the innovator gets there, we've got solutions.
Welcome to our conversation with Bob Pearce, the Associate Administrator for NASA's Aeronautics Research Mission Directorate. So this is another one of those podcasts where, with Bob's vast experience and given his leadership and portfolio at NASA, and given some of the recent NASA announcements, like the Sustainable Flight Demonstrator, we had to really think through what categories of aerospace, aviation, and advanced air mobility where we really wanted to focus. So we think you'll enjoy our talk with Bob in the areas where we did decide to focus and to be able to get some real depth of conversation in these areas. Bob talks about how NASA synthesizes a picture of the future in collaboration with thought leaders, and then helps to remove the challenges to make that future happen. What an important and meaningful role for NASA. And for those of us who have worked with or alongside NASA through the years, we can point to many successes as they execute that mission. We start with, a little bit surprising to me, around supersonic. And Bob talks about how it's a point of frequent discussion of NASA. Then we get to what is 35% in a much larger part of his portfolio, sustainability, the importance of getting to net zero, and the 3 strategies to achieving a fully sustainable aviation system. And for a number of reasons, I found this to be a really meaty, important discussion. In a world where I feel many are making questionable claims about how their actions are improving sustainability, NASA, as they almost always do, focus on what is important and what is hard. And as such, this discussion of their steps to a more sustainable future is worth every minute of your time. Bob talks about where NASA will and won't get involved in advanced air mobility, including how NASA is helping to facilitate a safe, high-density air traffic system. I like Bob's constant focus on how NASA focuses on tackling problems that are beyond where industry is focused today. We discuss what drove the creation of the Small Aircraft Transportation System, or SATS, 20 years ago, why it didn't work then, but why AAM may work today, including the level of automation we have today and what can evolve in the coming years, including the timeline for potentially fully remote pilots. We discuss UTM and Sky for All, what it is and NASA's role and timeline, and again, the role of automation, given the density of air traffic that will be coming. And listen to Bob's response to Luka's question of how UTM moves from where some would say is awareness today to true management. Next, Bob discusses the Sustainable Flight Demonstrator, why and how it was created, the cost-sharing partnership with Boeing, and he also discusses some of the questions that have evolved since that recent announcement. Given Bob's role with NextGen, we had to ask about what Bob feels were the best success and disappointments of NextGen, and his selection of one standout program, which, as it turns out, I was actually hoping he was going to say. Finally, listen to Bob's recommendations and advice to innovators. But don't skip to the end. This is one of our shorter podcasts, and it's worth soaking in every minute. Many thanks to Bob Pearce for joining us, one of our great American leaders. And to our listeners, we hope you enjoyed this important and enjoyable discussion with Bob Pearce as you innovate in the vertical space.
This episode of the Vertical Space podcast is brought to you by Avionics. Avionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let Avionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. Avionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace.
Mr. Robert A. Pearce is the Associate Administrator for NASA's Aeronautics Research Mission Directorate. Bob manages the agency's aeronautics research portfolio and guides its strategic direction, including research in quiet supersonic flight over land, urban air mobility, autonomy, highly efficient advanced air vehicle concepts, electrified aircraft propulsion, advanced materials, aerospace operations and safety, integration and flight demonstrations of aviation systems, and the nurturing and development of the transformative concepts for aviation. Bob served as acting associate administrator from August 2019. Prior to that, he was the ARMD's deputy associate administrator for strategy, where he led aeronautics research mission strategic planning to guide the content, strategic progress, and relevance of ARMD's associate portfolio, led review and evaluation of ARMD's budget and approval process. His first position in ARMD was as director for strategy, architecture, and analysis, where he established a strategic systems analysis capability focused on understanding the system-level impacts of NASA's programs, the potential for integrated solutions, and the development of high-leverage options for new investment and partnership. From 2003 until July 2010, Bob was the deputy director for the FAA-led Next Gen Air Transportation System Joint Planning and Development Office, or JPDO. The JPDO was an interagency office tasked with developing and facilitating the implementation of a national plan to transform the air transportation system to meet the long-term transportation needs of the nation. Prior to the JPDO, Bob held various strategic and program management positions within NASA. In the mid-90s, he led the development of key national policy documents, including the National Science and Technology Council's goals for a national partnership in aeronautics, research, and technology, and the Transportation Science and Technology Strategy. These two documents provided a substantial basis for NASA's expanded investment in aviation safety and airspace systems. He began his career as a design engineer at Grumman Corporation, working on such projects as the Navy's F-14 Tomcat fighter and DARPA's X-29 forward swept wing demonstrator. Bob also has experience from the Department of Transportation's Volpe National Transportation Systems Center, where he made contributions in the area of advanced concepts for intercity transportation systems. Bob has received NASA's Exceptional Service Medal for sustained excellence in planning and advocating innovative aeronautics programs in conjunction with the White House and other federal agencies. He received NASA's Exceptional Achievement Medal for outstanding leadership in support of the transformation of the nation's air transportation system. Bob has also received NASA's Cooperative External Achievement Award and several Exceptional Performance and Group Achievement Awards. Bob earned a Bachelor's of Science degree in Mechanical and Aerospace Engineering from Syracuse University and a Master's of Science degree in Technology and Policy from the Massachusetts Institute of Technology. Bob Pearce, welcome to the Vertical Space. Great to have you on. It's a great honor.
That's a pleasure. Thank you for having me.
So let's ask our first question. Is there anything that very few in the industry agree with you on?
So it's an interesting question. So I've always looked at this as it's really not so important what I think. My job is really to make sure that I'm talking to the thought leaders out there and synthesizing a picture of the future that aligns to the breadth of those thought leaders, and then really then focus on what are the challenges then in making that future happen. So if I think about now that said, there are aspects of the future which I think are more certain and aspects of the future which are more speculative. And so you do end up with a range of agreement and disagreement. So if I think about our portfolio, the thing that probably generates the most debate is around supersonics. And I think it comes in sort of one major flavor, I guess, kind of with a couple aspects to it. And that's really around the challenges associated with supersonics and especially achieving a sustainable supersonic transportation capability are so large, and given the needs of sustainability, the size of that challenge, why are we working in that area? And I think that's sort of the debate that happens quite often. Personally, I think that when I think about the long run and you think about the possibilities, supersonics could provide an excellent addition to overall mobility, but there are really big challenges that have to be overcome. But that's what we do. We're a research organization, and let's tackle the big problems. And the answer may be, we figured it out, and we've got a technology or capability that allows us to overcome those challenges. But maybe the answer is, we really can't quite overcome those challenges yet. And so in the end, it's about being objective about what we're finding and going with, the objective, facts and results of our research. So that's kind of, maybe it's a long answer to that question, but I think, that's really the way I look at this. And I do think that area of supersonics probably is the one that gets the most conversation.
It's funny, Bob. I was going to ask you later about supersonics, so I'm glad you called it out now. Yeah, I was a little surprised by that. I mean, with all the work that you're doing at sustainability, and even from a use case perspective, Luca and I have talked to people who have been critical of supersonic, questioning, at the end of the day, what does time really provide? And is there really a use case for, improve time, and are people willing to pay for it? And then to see NASA puts so much emphasis on it. So you must get that question a lot if you feel it's one of the areas that is most controversial or that many people don't necessarily agree with you on.
Yeah, there is a lot of questions. Let me just start with this issue of the balance of the portfolio. So we put most of our resources into sustainability. I think if you look over the next 5 years, something around 35% of our portfolio is focused on sustainability, and about 5% is focused on supersonic. So we work to achieve the right balance based on the priority of the challenges that the aviation system is facing, and certainly sustainability is the largest of those. And so we put the majority of our resources there. On the supersonic side, I view that as a long-term capability for the aviation system. And the reason I think it's something we want to continue to look at is because when we look at the market, there's certainly a transportation market to be had there. But I also think that just on first principles, our economy is built on communication and transportation. Those are sort of two fundamental pieces. And as we continue to advance our capabilities on the communication side, it really pushes on the capabilities of the transportation side. We can manage much more rapidly and agilely on the communication side, and you can have almost any good at your doorstep in a few hours. That's miracles of logistics and so forth that make that happen. But you think about the size of the globe and the integration across the globe and so forth. When you talk about those global distances, speed still matters. To get that, you got to overcome 4 big hurdles, and they're really clear and they're out there. One is landing and takeoff noise. They're low bypass ratio engines, and so they're going to generate more jet noise and so forth. And so you need to get landing and takeoff noise into the box. There's overland noise, so that's the sonic boom, right? So that's the one we're focused on right now, seeing if we can't develop an acceptable level of overland noise. So traditionally that's been known as the sonic boom, and that's, a telling name. We think we can get it down to a sonic rumble or a sonic thump. And so we're off proving that right now and hopefully objectively proving that would be an acceptable level noise to communities. And so that the regulators, FAA, CAO, and so forth, can actually develop a standard. The other 2 challenges are upper atmospheric emissions. So supersonic airplanes want to fly at higher altitudes, and so emitting emissions at higher altitudes. And so we need to understand the atmospheric science, and we need to mitigate those emissions so that there's an acceptable level of environmental challenge up there. And then probably the biggest one is the overall efficiency, right? So supersonic aircraft, because they generate wave drag, are going to be less efficient than subsonic aircraft. And today, if you were to design one based on current technology, you'd probably find that those were sort of unacceptable level of efficiency. But there's a lot we can do to improve the efficiency of supersonic aircraft. So those are, and so we'll work those. Now, because we're such a small part of our portfolio, we're not working on all those issues at once. We're sort of working on one at a time. And so it's going to take some time to solve all those issues. But again, I think this is more of a long-term capability than a near-term capability. So that's really, what we're trying to do. I think the other reason this is long-term is because in the end, I think the entire system has got to get to net zero emissions. That means your energy source is really critical to this, because you can only efficiency your way so far, right? You can't efficiency your way to zero. So you got to have an energy source that's net zero. And so the national strategy right now is increase the production of sustainable aviation fuels to get us to that net zero level. But we're starting from a few 100 million gallons today. We got to get to the goal is to get to about 5 billion gallons by 2035, I believe, and then 35 billion gallons by mid-century. So that's a huge ramp up, and so there's a lot of uncertainty. Can we get all the way there and so forth? And so I think for the near term, we've got to use those sustainable aviation fuels as efficiently as possible, and that's kind of the most efficient subsonic aircraft possible.
Just a quick follow-up on the supersonic. A lot of the things that you listed really center around clearly research and technological feasibility. Rightfully so, what one would expect of NASA. How much time and effort is spent in addressing the market desirability or the viability of the concept? And what are your evolving thoughts on how much of that supersonic aircraft the market can really absorb today or tomorrow?
Our job in doing research is to provide the information to industry and regulators to make the key decisions as to, obviously on the industry side, whether there's what the vehicle they can design based on the latest research really is compatible with a market. And obviously on the regulatory side is that vehicle can be designed. Is it safe? Is it environmentally compatible and so forth? Does it meet the kind of standards that society wants? So that's really our role. But we do look at the market in order to understand, is there a there? So, because this research takes time, it takes effort and resources. So let's make sure there's something there. So we have done some study of that. And there is especially on very long haul flights, there is a part of the market that would want to go faster. So I don't have the numbers in front of me, but, they are significant enough, in the order of 10, 15% of the demand that would maybe want to go that fast. Part of the benefit, right, of supersonics is you get, for long haul flights, better asset utilization. What I mean is, that same vehicle, if you're flying subsonically for a long, say, route between the US and Asia, you might get one turn on a vehicle. So one outbound flight, one inbound flight, whereas supersonically you might get two. So you get somewhat better asset utilization. Obviously, the folks get, the passengers get more speed, and so the time zone shift and everything can be a little bit better. So folks, especially for business purposes, would be spending less time on, could do a trip in fewer days, fewer business days, spend less time and less money on the ground and so forth. And that's where the market benefits come from is in the, not just the time saved in the air, but the time saved on the ground and the additional asset utilization you get from the aircraft itself.
Bob, let's talk a little bit about NASA and when you get involved in things. I mean, people often associate with space. So when you think about commercial transportation, you think about aviation, you think about advanced air mobility. What's the threshold that would cause you to get more involved with one of those areas? What's the checklist you use to say this is interesting, this is not?
Yeah, so we're meant to, we do research that's out beyond the sort of time horizon, risk horizon of industry. Aviation is a very long life cycle industry. You build a vehicle, a design lasts 30 years, and the vehicle itself will be in operation for 50 or 60 years kind of thing. So it takes a tremendous amount of technology, and it takes a large investment that will pay off over many decades. So that really requires a very long vision as to what the future requirements are, what those future issues are, and then an ability to invest in those. And, so when we look at an aviation market, we look at, are those conditions there where there is challenges to be overcome in the long run that are just beyond the capacity of industry to invest in, given that they already have challenging set of conditions that they've got to meet to develop a product. So, sustainability is certainly one of those that, getting to net zero, we're doing things like, how do we take electric propulsion and actually the application of electric propulsion to large aircraft. So say a 737 class aircraft that has 20 megawatts of installed power to propel the aircraft. Can you hybridize that for, and I can certainly go into it for, more depth, but could you hybridize that to get more efficiency on the propulsion system? That's a very radical change to that propulsion architecture. So those are the kind of things that the risk level that industry would take without some long-term, without some of that research to add some confidence to it would just, be beyond there. They wouldn't make that investment. On the advanced air mobility side, what we're seeing is lots and lots of money going into vehicle development. So we have no reason to jump into helping them on, helping all the various organizations on specifics of their vehicle design. But if you think about the long term, right, they want to get through certification, they want to get into operation, and then they want to be able to scale. Well, that means you have to have an air traffic system that enables them to fly at high density. That means you need to have safety management systems that enable us to prognostically understand risks and hazards before they become incidents and accidents, so that from day one, this advanced air mobility system is as safe as, an airline system. So that's had decades to become as safe as it is. So those are the kind of things, those are problems that are out beyond where industry is today. But if we work on them, try to get to solutions when the industry gets there in, 5 years, 10 years, those solutions are available and can be implemented.
Bob, on the topic of sustainability, you said currently that's about 35% of your research portfolio. How has that evolved over the years relative to perhaps advanced air mobility, and specifically on sustainability? If we're looking for the greatest impact, what do we need to focus on, we as an industry?
Let me start with the focus first, and I'll talk about how we got to where we got to. So there's three broadly accepted strategies for achieving fully sustainable aviation system. The first is technology, right? So that's new aircraft designs that are more efficient than today. The second is sustainable aviation fuels, or new low carbon energy sources. And then the third is operations. So if you've got very highly efficient aircraft, and if you're using sustainable aviation fuels, you want to operate those vehicles as absolutely as efficiently as possible. So you want the most effective air traffic management system that gives you optimal trajectories. So those are the three strategies. So for how we've got to where we've got to is kind of a story of research, right? So we've been looking at this challenge for 15 to 20 years. And the reason part of it's just the heritage of what we do, right? That's more efficiency, more fuel efficiency and so forth is just one of those bedrock kind of principles in aviation that's always been there. So we've always looked at what are those next generations of technologies that can get you to higher levels of efficiency. So probably starting about 15 years ago, we started some studies around, okay, so what would future vehicles look like that could be much more highly efficient than they are today. So think, 25, 30% more efficient than today. And so we did industry studies, we did our own internal studies and so forth. We had a range of vehicle configurations that could deliver that in the technologies that enable those configurations. And we just studied those, and we continued to study more fidelity. We did wind tunnel tests. We did methodology developments. We looked at particular technologies, enabling technologies that would have to be developed, and started low TRL technology development on those things, until we got to the point just recently where we had a suite of technologies that really were at that kind of moderate TRL 3-4 that, based on our both industry analysis and NASA analysis, we thought were the most promising. And so we decided to go forward with projects that would bring them to higher TRL, to TRL 6, which is around the level we get to for transition to industry. And so the four we're working on is, one is on the vehicle side, what is that more efficient vehicle configuration that has a path to the market? We've been working on several things like blended wing body, transonic truss brace wing, and others. We did a large and so those we had matured a bit, and we did a competition to say, okay, industry, what do you think are the best ones, and what are you willing to put into it? And we just recently selected our sustainable flight demonstrator, which is a transonic truss brace wing and a cost-sharing partnership with Boeing. We're also, because vehicles are, there's been a transition to composite structures in the industry, and for the next generation of vehicles, especially single-aisle vehicles, want to be produced at very high rates. Think 50, 60, 70 a month. And today, composite aircraft really can't be economically produced at those rates. And so we started a project called High Rate Composite Aircraft Manufacturing to reduce the cost of production of composite aircraft, so that we could, if we had this very efficient single aisle type aircraft, it could be produced economically at those rates. On the propulsion side, we're doing two things. One is on the core of the turbine, where you turn fuel into energy, into propulsive energy. Let's focus on the core. Let's shrink it, and let's make it more thermally efficient. So it does two things when we do that. One is the thermal efficiency means you get more of the energy out of the fuel you're using, and you're turning that into useful propulsive energy. So let's get that up. That means you're getting more out of the fuel. And then by shrinking it, by making it smaller, you actually increase your bypass ratio. The bypass ratio gives you your propulsive efficiency. So the energy you're getting from the propulsor, the big fan out in front of the engine, right? So by shrinking the inner core without increasing the outer diameter of the nacelle of that fan, you actually get better bypass ratio. And that bypass ratio is directly proportional to your propulsive efficiency. So by focusing on the core, we get better thermal efficiency and better propulsive efficiency. So that was a win-win. And then we looked at this, can we create a hybrid engine? So put about 1 megawatt of electric propulsion power onto a turbine engine. And the reason you want to do that is today turbine engines are designed for top of climb. That's where you have to put the most work out of the engine, the most power on the engine to get to top of climb. And then once you're at top of climb and you're cruising, you put the throttle back and you cruise. Well, if you're designing for that condition, you're sort of over-designing for cruise. Well, so if we can take some of the work off the turbine, put it onto an electric motor that's also driving that big fan, you can optimize the turbine more for that cruise condition and get more efficiency out of it that way. So on the vehicle side, we're looking at maybe about 10% improvement in efficiency. On the engine side, maybe about between the core and the hybridization, we get maybe 15, 20%. So we're looking at upwards of 30% for the work we're doing in our what we call the Sustainable Flight National Partnership. Those 4 key areas. We're also working with FAA on improving trajectories so that any new vehicle is going to fly the most optimal trajectories, and the ability perhaps to avoid contrails, which is another big greenhouse gas issue. It's actually, in the near term, in the short term, it's actually more impactful than carbon, but it's obviously an ephemeral effect. And so if you can avoid contrail formation, then you avoid that greenhouse gas altogether. And then the other piece is the ability for engines to operate on 100% sustainable aviation fuel. So we work that as well, and we do some atmospheric characterization. So those are all the pieces of our sustainable aviation portfolio. Like I said, it's about, on the order of 35%. It also includes university work we're doing. So we're giving universities the opportunity to come up with their best ideas and develop those ideas as well. So that's generated a lot of excitement at the university level and with students. We get a whole new workforce coming out that's ready to work on sustainability issues in the industry. So we're trying to be as comprehensive as possible.
I want to talk a little bit about the UTM and Sky for All in just a minute. But as we think about AAM, we think about eVTOL, what are the similarities with the small aircraft transportation system of the late 90s and the 2000s? What's the same and what's different, and why is AAM more likely to happen where SATS was not as successful?
So I think the similarity is with SATS is element of advanced air mobility, which you can think about as regional air mobility. So it's kind of small airport to small airport, providing regional, what I think we still do call a thin haul leg for a regional transportation. And then the thin haul just refers to the fact that you're talking about relatively small markets, but if you can have a small vehicle that's very efficient and affordable, it becomes affordable to provide a service that passengers would pay for. So that was the idea on SATS. Let's fly small airport to small airport using advanced small aircraft. I think, so that sort of consistent with an element of advanced air mobility, which is focused on that same market. The differences are that today, the big push on the propulsion side is on electric. And back in the SATS days, that we just we weren't mature enough to really push on the electric propulsion side. And electric can be substantially more efficient, but maybe more importantly, you can develop new vehicle configurations that are much more efficient. So like what we're doing with the X-57, which is let's put distributed electric propulsion across the leading edge, and you get a much more efficient wing out of that. We can talk more about that, but suffice to say, you get a much more efficient wing. And you get this very efficient propulsion system, and so you get electric motors are highly reliable, and so your maintenance costs go down. So there's a lot of goodness to now having electric propulsion available to us. The other piece is automation and autonomy. In the SATS days, there was a lot of push on automation, but I don't think we were at the point of being able to have a vision for the level of automation that we can today. You certainly want to get down to single pilot, maybe fully remote piloted aircraft, maybe one pilot to many aircraft to really get the level of affordability up so that you get the price way down. And so I think there's just elements of technology that are ready today that weren't quite ready during SATS. And of course, for advanced air mobility, there are other types of markets that really couldn't have been envisioned when we were thinking about SATS. And that's more the urban air mobility focus, eVTOL, operating in and around urban areas in new and unique ways that were not part of the SATS vision.
What are some of the most contentious issues in the discussions around autonomy in your group?
Well, the issue really is you want your automation. So it's a requirement, right? That, if you want to get to a fully scalable system where you're flying maybe a few passengers or a small amount of cargo at a time, to make that affordable, you really do need to get to a more highly automated system. So over the long run, you need to get there. But the key for us is we know that you can automate a vehicle system, but the question is, how do you do that with guaranteed safety, right? And so that's really our focus, is on all the elements of safe automation and safe autonomy, so that not only do we make sure we're as safe as possible, we want it to be safer than would otherwise occur. And so that's really the, so all the off-nominal conditions that will be realized in, as just a normal part of operations. When you're doing a lot of operations, there will be anomalies, there will be off-nominals, and so all those have to be handled, the failure states and so forth. And also just the ability to certify those kinds of systems. So advanced verification and validation tools that give the certification authorities confidence that automation system actually is safe, will provide the safety that's necessary for operations, will be able to handle all the off-nominals and so forth. So having those tools that provide that confidence to the certifier. So we're working on that. The other thing that probably just doesn't get as much attention is, I think, on safety management. So you think about why the aviation system is as safe as it is today. It's because of the decades and decades of experience and the unfortunate incidents and accidents that have occurred over time. And every time there's a serious incident or if there's an accident, there is a tremendous amount of analysis and focus on that to make sure we fully understand the root causes and we fix those. So we mitigate all those. And so you don't get those types of accidents. And over time, as you fix all those issues, it becomes harder. There's less opportunity for things to get away from you and for incidents and accidents to happen. And that's why the system is as safe as it is today. But if you think about an advanced air mobility system, it very much is a different system. It doesn't have that same history with traditional aviation. And so how do you avoid having to go through all of those lessons and the incidents and accidents? And so you got to get to prognostics. That's the key, is to have a fully prognostic system. And that's going to have to be highly automated as well. You've got to be able to discover through data mining and so forth where risks and hazards are popping up. And through automation, you're going to have to, in some cases, you're going to have to find mitigations, what we call in time, right? In time to avoid the incident or accident. So that could be a long term, that could be a short, that could be a matter of minutes or seconds, but that's what you want to do to make sure that this system is safe from day one. So I think that's a big element of automation that oftentimes doesn't get talked about.
Bob, you mentioned fully remote pilots, and there's some people who believe that the eVTOLs won't really be profitable until we have fully remote pilots. What's your guess as to when we'll see that as part of a safe air traffic system going forward?
My guess would be after the first certifications of eVTOLs, which will be piloted. I think you're looking at probably 5 years, because I think what we at that point, you've got vehicles operating. You can start to both, you'll understand the safety of those vehicles. And even the piloted vehicles will have a lot of automation on board. And so we'll start to understand the safety of the automation. We'll have all those, we'll start to build up that database that's required. And you can start to do things like having remote operators in the background, even while pilots are on board and so forth. And so you've got opportunities to start doing those kinds of, shadow type operations that start to then build up the data required to give you confidence that you can move to remote pilots and so forth. So I would see maybe optimistically about a 5-year window where, with some focus after those initial certifications, we could probably be at a point where there's confidence that that kind of a system could be certified.
I was expecting about 10 years after that. So,
well, I'd say that's a bit optimistic.
Bob, let's talk a little bit about UTM and Sky for All. Clearly a role that is appropriate for NASA. Talk about what is it and why is it important and what's the role of NASA?
Yeah, so we have for decades been a partner with the Federal Aviation Administration in the development of advanced air traffic management capabilities and tools and so forth. And a lot of what's in the next gen system is based on research and development, from us at NASA. And so we've got that traditional role. So the vision for, and largely we have completed the kind of work we plan to do for next gen, and we've transferred that to the FAA. We'll remain involved and we'll continue to support the FAA in the continued rollout and development of next gen. But we have set our eyes on the future. And so if you think about that future, it's going to be, today it's really dominated by the airlines and the type of operations they do, in addition to general and business aviation traffic. But if you think about the future and with drone operations, small UAS, medium-sized UAS, eVTOLs, eCTOLs, high altitude, long endurance vehicles, maybe supersonics out in the future, maybe even hypersonics out in the future. This system is going to become more complex in order to meet the needs of all those business models and those, the performance of those vehicles that are going to fly in the NAS. So that's what really we're focused on. The FAA has in their next vision, they call infocentric NAS. It's really about, based on what we were able to prove in UAS traffic management, they have coined a term, extensible traffic management, which is the idea that each of these kinds of things like UTM or advanced air mobility or high altitude, long endurance, whatever, they could use those same principles of UTM to create a system that would enable that kind of an operation, but be fully interfaceable to the NAS, right, to the kind of the central air traffic management system that operates today. But do that as a lot of those could be third-party services, and to enable those things to go faster. So you can start to envision that with a more modernized network architecture, with a lot of data sharing and a lot of third-party services, you can start to support these kind of operations. What's missing, I think, and what our vision for Sky for All is, that you're going to need, again, to have greater levels of automation, because the complexity is such that having human controllers sorting out traffic, and now much more complex traffic than maybe was occurring in the past, would just really be beyond what would be feasible for the kind of densities of traffic and complexities of traffic that are coming. So what we would envision is overlaying machine learning and automation, autonomy, AI, those kinds of things into the system to support the human in enabling the complexity and the density of future traffic that will be coming, and doing it safely, right? Which is absolutely the bedrock value, right? That all of this be done safely. So we're already doing some work that we've demonstrated. And specifically, if you take an automation, each airport is different, each sector, each air traffic control facility is different. And so we build these automation tools, and they have to be adapted to the airport, adapted to the air traffic control facility. And what we've done is built some tools that enable using AI to help with that adaptation, so we can quickly take an automation tool and adapt it to a new situation. So that's a step in that direction. So we're already working towards those things. But Sky for All is kind of more of a mid-century, let's really get towards that, a system that is really uses machine learning, AI to supplement the human to enable, again, the density and complexity of all the kinds of operations I mentioned earlier.
When we talk about UTM, it really feels like it's more of awareness at this point rather than true management. So what's the path to true management, and how do ATM and UTM interact? What are really the interfaces beyond lanes authorization?
Yeah, so you're right. So that there is, there's another step up that we need to go from a UTM to something that would say manage an advanced air mobility system, and there's obviously a couple of reasons for that. You're going to be at higher altitude, and you're going to start really interfacing with the NAS as it's configured today with traditional aviation. And you're going to be, if you think about an eVTOL, it's going to be taking off and landing from vertiports. UAS can take off and land from in a very highly distributed manner, so you don't have those central places where traffic are coming in and out of. So you need to do the kinds of things that we've developed automation tools for in the past, the sequencing and spacing into a vertiport, making sure that that there is separation is assured, and all those, so you have to overlay those more safety critical functions into the system. So there's a lot of work to be done to establish separation minimums, and for establishing how you would do how that separation would be assured and so forth. And that's the kind of work we're doing today in our simulators to actually develop those algorithms to enable what's now called PSUs, provider services for UAM versus UTM, so that all those kinds of critical functions can be solved and implemented. And then of course there's, in the nearer term, right, there is the interface with next gen, or with the current system, because one of the use cases that I think one of the initial use cases that I think you're going to see is, operation from, say, a downtown vertiport to the hub airport in the vicinity. So, and that, of course, the hub airport's sitting in Class B airspace, and today there are many places have helicopter routes, fixed helicopter routes that go in and out of those. And so the EV tolls can start on those, but that's going to have to be expanded. And so we're looking at things like automated corridors and so forth that allow more regular and somewhat higher density routes in and out of big airports and have an interface to the controllers with that control that airspace. And so those are some of the things we're doing in the near term that we see as being initial solutions to get the industry operating. But again, we're looking at more general solutions that tackle those hard problems for the longer term.
Bob, speaking of UTM, Sky for All, and the integration based on Luca's question of UTM, what would you say is a role of innovators here that you think could supplement what's being done by the FAA, by NASA? What challenge would you give to them that they may be able to step up and provide?
We have operated instead of AEM community working groups, ecosystem working groups, that has brought the community together to talk about what the requirements are and the challenges, try to get to agreement on those things. The next step, I think, is we have to develop the concept of the automation architecture that underlies the operation of these vehicles in the NAS. And I think if we come together as a community and develop an agreed upon automation architecture, then what it does is it can unleash innovators to then look at aspects of that architecture and to start to innovate in those spaces. And NASA can also innovate in that space. But the thing it does is everybody is pointed in the same direction, right? We're all pulling the wagon in the same direction, and that's the key. Without that, I think there's going to be a lot of innovation. Folks are out there today. We've got hundreds of organizations involved in this space in one way or another. But it will take longer, right? If there's not some fundamental agreements on some aspects of how the system operates. And so I think that's the key to further unleashing innovators. The other piece is, and I think this really is another thing that we need to do better at NASA, is making sure that we're doing everything possible in our partnership with the FAA to validate and mature these concepts, architectures, automation platforms, and so forth, to the point where FAA can operationalize. So I think this is an area where I think we've done a really good job in the past, but I think we probably could have done better. And so I think we're learning, and we need to continue to get better at that, so that there's less of a gap in time from when things are proven to when things can operationalize. Because for the innovator, that's the problem, right? If there's they're running on private capital, and that can only last for so long, and so if there are long periods of time, then they can start to run out of funding, and we lose that the innovator, and we don't want to do that, right? Because that's a big engine.
Okay, let's go to a lightning round, given the time available. Okay. Sustainable Flight Demonstrator Project, you mentioned it. What was the most controversial part of that project?
The most controversial part of it,
what was the pushback you got from people that questioned NASA's role in that, and what's been the toughest question to answer as it relates to that project?
Yeah, I think it's getting folks to understand, because you look at it and it's going to look like a transport aircraft, and it's the question, well, why is NASA investing in a transport aircraft? It's not private industries. And I think getting folks to understand that this really is an experimental aircraft. It is one it's a configuration that has to be proven in flight before any kind of a commercial decision can get made. And that's another, once a commercial decision, that's another, 5, 6, 7 years of development. So this really is well out in front of a development decision. And it's getting folks to understand that this just happens to be the path to TRL 6. We don't do it often, but sometimes you got to do something big and bold and go out and build an experimental aircraft of that scale.
Simon Sinek interview, I really like that. Your interview with Simon Sinek, what was your biggest takeaway from it?
I think it's about building that trust and supporting the essence of leadership, of supporting the folks that are going to make this work. And I think having vision, generating trust, and then supporting your folks to run hard and get the job done.
I'd encourage other people to listen to that or to watch that interview. It was terrific. Thank you. Next Gen, what was the greatest success and greatest disappointment?
Next Gen, I think the greatest success is the fact that developed fundamentally I think the best partnership in government between NASA and FAA in the development and fielding of technology. The disappointment, I think, is just everything takes longer than you hope. And not every part of what could have been gets picked up. So I think we would have loved to see us go faster and do a bit more.
What was the best program?
The best program, just in general?
With the Next Gen?
Well, I think for FAA, their big bet was ADS-B, kind of fundamental to enabling the kinds of operations, and the kinds of automation that we are able to field today. So I think on that side, on our side, on the NASA side, it was what we did, I think, in what we called ATD2, or so the ground operations all the way up through getting folks to top of climb and into the upper stream, I think has been recognized as just a tremendous
most definitely.
Yes, but I hate to pick a child like that, because we did other things as well.
But very quantifiable benefits with that program. Yeah. Okay, so who's the most colorful personality you've seen in your many years in Washington?
Back in the Next Gen days, we had a great airline panel, and so like Herb Kelleher was on that, and others. I mean, they were just some of the prior generation of airline CEOs were pretty colorful characters. Kind of closer to home, I had a boss. I think you learn a lot from everybody. Sometimes it's good, sometimes it's bad. There was one of my prior bosses, Sam Veneri, was just a tremendous visionary. But boy, he was definitely colorful. He was all over the map sometimes, but he was one of the best visionaries I've ever worked for. That's
great. So you got a bunch of innovators on the line. One piece of advice would you give them in working with NASA or advanced air mobility or aviation? What would you tell them?
I think understanding where we work, which is we can't go as fast as a small, lean, innovative, an agile innovator. But what we can do is if we can pick a point in the future, let's look 5 years out, 7 years out, 10 years out and say, this is where we need to get to. NASA can take on some of the really hard challenges and work through those so that by the time the innovator gets there, we've got solutions. But they'll always be able to go on a day-to-day basis, go faster, be more agile than we can.
Bob, as you prepared for the podcast and you heard that it was for mainly innovators, I mean, I've seen and we've read a bunch of your interviews. What's the one message you wanted to give to this group?
I think often coming in from other industries where you can go a bit faster, aviation it is going to take longer. The investment levels are going to be higher. And I think that's fundamentally because safety is core. There's no compromise on the safety side. And so I would just say, get folks that are expert in aviation and in safety on your team and plan for that being, something that you've got to pay attention to every day.
You run a great organization, Bob, and it's a real pleasure to have you on. So thank you for joining us.
Oh, it's been my pleasure. Thank you so much.
All right, that's a wrap for today. Thank you for listening to the Vertical Space Podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.